currently recording the lesson. Again, a copy of this recording can be found on YouTube after we finish class. And I will share with you the whiteboard. Let's get started. So start here. So our lesson today will be 1.5, the limit of a function. Key section in the understanding of calculus. And here's the deal. So let's say we have some sort of graph in the xy plane. Very simple concept, by the way. Some sort of graph, something like this. And somebody's asking you, so if you take a point here, and the point will be the point 3 here, let's say. What happens if you take a sequence of points getting closer and closer to 3, like something like this that gets closer and closer to 3, but not exactly 3? Well, we can look at the values of this function and we can realize, oh, maybe the value of this function is, the values are measured on the y-axis, folks. That's why we had that discussion of the x and y axis and graphing and stuff. So values are measured on the y-axis, and if you look at the values of this function on the y-axis, right, there's this one here, and let's put this one here, the last one. You can see that the values of this function are these here measured on the y-axis, and they get closer and closer to the value of my function at 3. So this is f of 3 over here, whatever this number is here. So you can see that these values are getting closer and closer to the value at 3. But that is not always the case. That is not always the case. So when we see this kind of behavior where the values of a certain function approach a certain number, we say that we have a situation of a well-defined limit. Now, let me give you a numerical example. Let's say our function is f of x equals x plus 2. And let's say we want to calculate this limit. So now copy with me this symbol, folks. This is a symbol that I haven't defined yet. I just intuitively sort of said something about the limit here. So copy with me this symbol. So LIM here as x approaches, let's say a number like 3 of x plus 2. What would that be? So we intuitively can say that as the values of x approach 3, the values of this function x plus 2, where you add 2 to x, will approach 3 plus 2, which would be 5. So we would say that. Now let's convince ourselves that that is the case. In other words, if we plug in here numbers, values of x that are very close to 3. So let's say 3 will be here, and I am plugging in numbers like what the number would be close to 3. For example, 2. I can define my notion of being close to something, essentially starting with 2 and then giving value like 2.5. 2.5 is certainly closer to 3, and then 2.9, and that's going to be even closer to 3, and then 2.99, let's say, that's going to be even closer to 3, and I can squeeze in more values like that. You can see here that these numbers, so what's their characteristic? They get closer and closer to 3. And then we can study the values of x plus 2. And the values of x plus 2 corresponding to these chosen values of x are 4. Then if you add 2 to 2.5, you get 4.5 over here. And if you add 2.9 to 2, you get 4.9. And then 2.99 add 2, you get the 4.99 and so on. So these values are really getting close to 3. We can say that, yeah, well, it's kind of obvious here that these numbers are getting close to 3. And this is a very simplistic example, but that's the key in understanding today's lesson. So if you understood this example, well, when I get values of x getting very close to 3, and I calculate the values of x plus 2, and I realize that these are also very close to 3, well, guess what? I'm going to say that the limit of x plus 2 as x is approaching 3, I'm going to say that that is equal to, I'm sorry, so the value here, I'm sorry, folks, the value is not getting close to 3, it's getting close to 5 here, right? 4.9, 4.99, of course, close to 5. So I'm going to say that the limit here, let me just delete that, and I'm going to say that the limit there is going to be 5. So this is a simplistic example, folks. But again, if you understood, this is key to getting the notion of limit. This simplistic example. Let me give one other example that's slightly more complex. In this example, let's say we have a function. This is another example. Let's say we have a function f of x equals let's say x squared minus 1 divided by x minus 1. Now this is going to be a non-obvious example, although we did something that should remind us of this type of fraction. So let's say if you want to calculate the limit as x approaches 1 of x squared minus 1 over x minus 1, what do you think this limit will be? Well, it's not very obvious from the formula here, because if I start getting 1 in this formula, like I did in the previous formula when I had x plus 2, and I could substitute 2 simply in the formula, or 3 or whatever I had there, I cannot simply substitute 1 here, because I would get 1 minus 1 over 1 minus 1, and that's going to be 0 over 0, and that's not something that you want to do in math. You don't want to divide by 0. So this is a not so obvious example. However, this can be treated numerically like we did with the previous example. So we choose values of x that are very close to 1. Now, what numbers are very close to 1? Well, something like 0, for example, would be considered very close to 1. Notice I'm starting from the left. Then you can choose another number like 0.5, and that's even closer to 1. And then you can choose a number like 0.9, and that's even closer to 1. And then you can choose a number like 0.99, and that's even closer to 9. And then you can choose a number like 0.999, and that's even closer to 1. So these numbers over here at the top, they are getting very close to 1. So the question is, can I conclude the same sort of thing about the numbers x squared minus 1 over x minus 1? If I calculate the values of this function at these numbers here, can I conclude that all these numbers down here get very close to something? And the answer is yes, but that's not going to be such a simple calculation, because once you get past 0, where it's very easy to see that 0 minus 1 over 0 minus 1 is negative 1 over negative 1 or 1, the other numbers here need to be calculated by making use of a calculator. So what I'm going to do, folks, I'm going to show you how to do that with decimals. Now I remember this problem. I'm going to stop sharing that screen, and I'm going to go straight to decimals. Now, unfortunately, decimals is not open, so it's not recognized by my page here. Okay. 1 second, folks. Let's try again. All right, there we go. So let's go to this Freddy the Falcon here. Now let's access decimals. And when you access Desmos, what you need to do is to go here. I'm hoping everybody gets to see the page with Desmos here. And we're going to create a table. So we're going to create a table here, exactly like we did earlier. Now, the only difference is that these tables here in Desmos, you got to be a little careful with them. So first of all, you want to relabel your letters here. So I'm going to call this, you know what, hang on a second. Before we create the table, let's say what the function was. So our function was f of x, oops, f of x equals, sorry about the beginning part. So I'm going to say here x squared minus 1, right? That was the beginning part, divided by x minus 1. So that is my function. And forget about this graph here. You don't need that for the moment. So, so this is our function. And we want to do a table now, right? We want to calculate here. So let's write a note to ourselves here, first of all. So as you can see, what I did, I clicked here on the plus sign here, and I clicked on note, and my note is the following. So we want limit as x approaches 1 of f of x. So we want to see what the values of f do, how do they behave when x approaches 1. And I'm going to do the limit calculation here. So what I'm going to do, I'm going to add an item. So pay attention, folks, because this is something that you want to do on tests as well. So use this Desmos, which is very powerful. I told you, very powerful calculator. You don't have to use TI-86s and anything like that, because this one really comes up with necessary tools. And I'm going to do a table here. And the only thing you want to be careful with this table, this is kind of, you know, it's a piece of software, so it's a bit sensitive with the type of notation that you use. So always a good idea is to relabel your thing. So call it t, the variable here, instead of x1. And over here, put f of t. Oh, oops, not f of x, I'm sorry, f of t. So I'm going to say here, and then this is going to populate the table automatically. So remember that the values that we wanted to put there were 0, and that's going to populate automatically that f of t is 1. And then we wanted to put 0. What was that, 5, and we get that the value of f of t of this function here is 1.5 automatically in the table. And you want to put 0.9, and that's going to tell you that the value of f is 1.9. And then you're going to put 0.99, for example, and that's going to give you 1.99 here in the table. And that's going to put, let's put 0.9999, a large number of nines, like 4 here, and that's going to give you 1.999. So you can conclude, folks, here, as you can see, t is getting very, very close to 1 on the left side of the table. And the values of f at t on the right side of the table are getting very close to what, folks? Tell me in the chat here if you notice any sort of behavior here. If you can conclude with certainty that, well, the values of t are getting very close to what? What number is that? That's right. So Sammy said that they are getting close to 2. That's correct. So we are going to say, folks, based on what we see from this table, that the limit as t approaches or x approaches 1 of f of x is going to be equal to 2, because, you know, based on this table, we saw that type of behavior. So over here, I'm just going to copy these values from the table, from my table. So we said here we had when x was 1.5 here, and this is 1.9, and this is 1.99, and for this number here, 3 or 4 zeros, I don't remember, 1.999 and such. So yeah, this limit is going to go to 2. So that's going to be my answer. That's a question mark here. So I'm going to answer, well, the limit as x approaches 1 of f of x, which is x squared minus 1 over x minus 1, is actually equal to 2. So that's going to be my conclusion here for the limit in this case. And I'm going to do yet another example here that's going to be even more complex than this one and even less intuitive. And that example is going to be the following. All right, so let's do another example here. Just to turn the page here. All right, so I'm going to take the function f of x equal to, and look at this one, folks. So this is going to be something. So I'm going to do sine x over x. And I'm going to do this following limit. Limit as x approaches 0 of sine x over x. Now remember, x is measured in radians in this case. Is that important? Yes. Why is that important? Because look here, folks. The value of sine. Let's think a little bit about this function. The value of sine is a fraction, a proportion, which is a number without units, right? So sine is the opposite over hypotenuse, and if the sides of a triangle are measured in centimeters, for example, or inches or something like that, when we do the quotient of two of them, so we have 3 inches divided by 4 inches, the quotient, the inches will cancel out, and the quotient will be a number, a proportional number, without any sort of units. So this one doesn't have units. What this one does, the bottom part does have units. So it's the way you measure the angle, whether you measure it in radians, and the units will be radians. You measure it in degrees, the units will be degrees. So it matters what you measure your angle. But if we measure in radians, I claim that the value of this limit will turn out to be 1. Now, this might be a little surprising because, well, at least it's unintuitive, because there's no good reason why we would say here, we will find a reason, but there's no good reason why you from the get-go, you would say, oh, this limit is going to be 1. So let's calculate this limit by using a table of values. So I'm going to stop sharing the whiteboard here, and I'm going to go back to Desmos, which is going to be our big helper today. And we're going to go to Desmos here, and we're going to remove all of that, all the stuff that we did earlier, and we're going to say here, f of x equals sine x over x. All right, and this is going to be my function. And, I'm going to turn off that thing there, and I'm going to say here, let's calculate the limit. So again, I'm going to put a note to myself, limit as x approaches 0 of f of x. And I'm going to calculate the limit by using a table of values. So again, click on the plus sign here, use a table, wipe out these letters that the program originally provides you with. Those are very confusing. I don't know why they do that sort of thing. And you put a t here, and again, f of t here. So at the top, remember, folks, to do this sort of thing, to do this change of letters there. Otherwise, Desmos will be really confused. So, so what I'm going to do here, I'm going to say, I want numbers x approaching 0. So let's do a bunch of numbers approaching 0. For example, 1 approaches 0. And, well, so before we do that, though, let's actually make sure that x is measured in radians. So to do that, you can go here where the graph settings are. You can say here, on the x-axis, I want this to be measured in radians. So what I'm going to do, okay. It shows me radians here, but I want to put, oops, sorry about that, my screen is kind of small, so it's either cover one thing or the other if I move things around here. All right, so on the x-axis, I want a step, just to make sure, I want a step of pi. All right, so over here should be okay. So what I have here is actually okay. Well, I want to put, instead of 1, I want to put pi. And it says here that the value of my function is 0 at pi. Let's see if that's the case. Yeah, it is the case because look, folks, here sine of pi is 0 and pi at the denominator is, pi, so it's 0 divided by pi, and that's going to end up being 0. And now we get a sequence of numbers getting very close to 0, but now because remember we take radians, we want to do, multiples of pi. That's more intuitive. So pi that I took here was actually 180, so it's a very large number. In degrees, if we look degrees, but we're going to make that smaller. So we're going to do pi over 2. And when we get pi over 2 here, we get this value, again, unintuitive value. So let's see what happens here. So sine of pi over 2 at the top will be 1. And that's a known value. So that's one of those that I told you to review. And pi over 2 at the bottom will be pi over 2. So it's 1 divided by pi over 2. And probably that is this number. All right, let's take some further values. So let's take pi over 6. That's even closer to 0, right? So pi over 6 is 30 degrees, folks. So that's, you divide 180, right? Pi is 180 degrees. Dividing 6 parts is 30 degrees. So you can see that this number is larger than the one before. And then we get numbers that are even closer to 0. So as you can see, pi over 6 is a very small number. If pi is about 3.14 and 6 is 6, obviously. So 3.14 divided by 6 is about 1/2. All right, so let's do the next thing. Let's do pi over 12. Well, if we do pi over 12, this number, pi is 3.14, 12 is 12, so 3.14 divided into 12 parts is approximately 1/4. So, so you can see that the value of f is even higher than the one before. So it looks like, at least from these examples, it looks like the values of f are higher, getting higher. And let's do a very small number. In other words, let's divide pi into maybe 120 parts. And if we do so, we really get a number that's really tiny because pi is 3.14 divided into 120 parts is approximately, this number pi over 120 is approximately 3 in 120, so it's like 1 in 40 part. Okay, so so it's 0.02 or something like that. All right, so it's a very small number. So these numbers on the left, they approach 0. Look at these numbers on the right. So they approach, folks, they approach 1. As you can see here, 0, 60, 0.63, 0.95, 0.98, 0.999. And if you increase the denominator of a fraction here, so you do pi over 1,000, let's say, that number is going to grow even higher, even closer to 1. It's going to be 0.99999. So based on the observations from this table, folks, we can conclude, and you can see that it even plots these points on the graph. If you look at if we turn on the graph, oops, I turn on the graph here, you can see that these points are plotted on the graph of sine x over x. So it plots these points and it shows you that they really, the y value is getting closer to 1. So these values are f of t's. So we can conclude, folks, and I'm going to stop sharing over here, and we can conclude here, start sharing this board, that, that the limit that we're talking about here, the limit is x approaches 1 of sine x, x approaches 0, I'm sorry, 0, sine x over x is going to be equal to 1. So this is my conclusion based on the observations of that table. Based on the table of values that we did earlier in Desmos. So, so now let's look again at some other things here. Let's say we want to do so this would be example 3, I'm assuming. Yeah, 3. And let's do another example, example 4 here. And let's do the limit. Let's do another function, f of x equals, how about this one? Sine of 1 over x. Let's see what happens with this function. What is the limit of this thing as x approaches 0? So if we do limit as x approaches 0 of sine of 1 over x, what is the value of this limit? Well, let's go back to Desmos, our very helpful calculator, and let's see what we can conclude with this function. So I'm gonna turn off that thing, turn off this thing, and turn off this thing, and I'm gonna write here f of x equals sine of 1 over x. And whoa, look at that, what happens there. So if you look at the graph, you will see there's something unusual here. So so the more you zoom in, the more you'll see that, oh, there's a bunch of things. There's a point here that goes up and down and up and down and up and down. And it's like, look at that, there's a mess here with this function. So what happens here, folks? What do you think happens with this function? What is the limit? So let's see what happens. So I'm going to do a note. So we calculate here the limit as x approaches 0 of sine of 1 over x. All right. And let's proceed with the table. So let's get our useful table and let's see what happens with this limit. Again, we wipe out the x and we wipe out the y here. And we write t and f of t over here. And let's give values to x. So let's give values like pi, for example. That's we start like we did before, and then we do pi over 2, and then we do pi over 3, and then we do pi over 4. And then we do pi over 5. And then we do pi over 6. Then we do pi over 7. Then we do pi over 8. And I can play with these numbers as much as I want. So I can do a lot of values of pi, pi over 9, and so on and so forth. So look at this here, folks. Look at this here. So I'm getting close to 0, right? Because these numbers are obviously decreasing, right? We're increasing the denominator, so we're getting very small numbers. And but my values here don't follow a clear pattern. So first of all, they appear to go higher and higher. They appear to go close to 1. But then I started going down, and there's 9.94, and then 0.79, 0.56, 0.27. So they get closer to 0 apparently. But if I do more values, pi over 10, I get even negative numbers in pi over 11. Look at that, even more negative numbers in pi over 12 and pi over 13. And look at that, even more so in pi over, let's say pi over 20. And look at pi over 20 is positive. So look at these folks. We get a bunch of positive numbers growing and then decreasing, and then the negative numbers, and then positive number again. What's going on here? So if we do pi over, let's say 50, let's say that, well, that's again negative number. And let's see if we do pi over 100. That's a positive number. So it's a mess here. All these table, folks, these values are all over the place. As you can see there, look at that. You can see them on the graph here. They're going up and down and up and down, and it's a mess. So, folks, if you run into a situation like that when the table tells you that there's no clear conclusion, and the table tells us this, that we go up and then we go down, so with the values, and then up and again down, and positive and negative and all over the place values, that really tells me that this example does not have a limit. And I can actually show you that this does not have a limit. So any number could be a limit value if you want. Any number between 0 and 1. I'll show you in a little later why that would be the case. But folks, again, if you don't notice a pattern when you get closer and closer to 0, it means probably no pattern, and you can conclude safely here that this function would not have a limit. Now, if you look at the graph, what happens with the graph, folks, so remember, if you want to have a limit as x approaches 0, it means that the y values of your point on the graph as you approach 0 would have to be about constant. But look at my y values, because this function is like an oscillator. It goes up and down and up and down and up and down. So no matter how much you get closer and closer to see it, look at that. So you can see that it goes up and down and up and down. This is a continuous wave of length of amplitude 1 going towards the origin, but it never decides, it never makes up its mind where should I stop, at 0 or at 1, or where exactly. So what happens, folks, here is that we can conclude with some degree of certainty that this function does not have a limit. So we can say here there is no limit. We can say there is no limit for this particular function. All right, so now how can we distinguish that there is no limit? Well, for that, we have to kind of be a little more rigorous about the definition of limit. And the definition of limit has a couple of aspects. First of all, so the definition of limit of a function at a number, let's say x equals to, I don't know, we did 0, we did 1, we did 2 and 3, things like that. So let's say x equals 5. I'm going to fix a number like that, x equals 5. So we say that the limit as x approaches 5 of f of x is equal to a number L if for every neighborhood, and I'm going to define neighborhood in a second. of L, we can find an open interval around 5 that F maps entirely in the neighborhood of L. So here's what I mean by that, folks. I mean, if I represent L here on this line, and I take a neighborhood like this, neighborhood meaning a very small interval around L. So L is over here, and I represent the starting values, the values of 5 over here. What F does, it takes all the values from here and it maps from inside this interval here around L. So no matter how much I shrink this interval around L, I always find a smaller interval, maybe around 5, that is entirely mapped over here inside this small interval around L. So that's kind of the intuitive idea around the notion of limit. So the values of F are very, very, very close to L, as the values of X are very close to 5. So that's the idea of a limit. Now, how can I prove that the limit of sine of 1 over x does not exist? So let's take another look at that. Oops. Let's take another look at that. So the limit as x approaches 0 of sine of 1 over x does not exist. So let me tell you why. The reason is, folks, if you give values of x equal to 1 over pi over 2 or 1 over 3 pi over 2. So remember that these are large numbers, the ones here, pi over 2, 3 pi over 2, or actually let me make them simpler. So let's do pi. Let's do pi, simpler multiples. So pi, 2 pi, 1 over 3 pi, 1 over 4 pi, and so on. So if I do the multiples of pi here in the denominator, then these values of x are obviously all very close to 0. So sine of x in this case is sine of 1 over pi and sine of 1 over 2 pi. Remember that x is 1 over 2 pi, and also sine of 1 over 3 pi, and so on and so forth. So these numbers are sine of pi, sine of 2 pi, sine of 3 pi, and so on, and sine of the multiples of pi. So this number here turns out to be pi, this number here is 2 pi, this number here is 3 pi, and sine of pi, sine of 2 pi, sine of 3 pi, and so on are all 0. So there we go. So we get a number, a bunch of values of x that are very close to 0, and sine of x is very close to 0. Is 0 actually at all those values. But then I can get another bunch of values of x, like the ones I started with, where you have here 1 over pi over 2. So this is my number here, 1 over 3 pi over 2, 1 over let's say pi over 2 plus 2 pi. So just to simplify things a little bit here. So sorry, this example is slightly more complex. Okay, so pi over 2 plus 2 pi would be 5 pi over 2, let's say that. And then we add the multiples of 2 pi. So adding multiples of 2 pi means adding 4 times multiple of pi's if we divide them by 2. So it would be 1 over 5 pi over 2, 1 over 9 pi over 2, 1 over, and then over here we have, yeah, you know what? I don't like that the way I wrote it here. So let's write this way. Let's write pi over 2 plus 2 pi, pi over 2 plus 4 pi, pi over 2 plus 6 pi. There we go. I hope this is easier to understand. So what's happening here in the denominator? So we add multiples of 2 pi in the denominator. When we flip these over, when we say sine of 1 over x, what I'm going to end up here, I'm going to end up with sine of 1 over one of these numbers, which flips over yet again. So for example, sine of 1 over pi over 2 plus 1 over, oops, 1 over, oops, sorry about that. Come on, eraser. All right. Sine over 1 over pi over 2 plus 4 pi, for example. So when you flip over this thing, it's going to end up being sine of pi over 2 plus 4 pi. And this ends up being 1, folks. So that's the main point. So sine at all these values here is going to be equal to 1 for all these values here. 1 over pi over 2, 1 over pi over 2 plus 2 pi, pi over 2 plus 4 pi, and so on. These are all numbers going to 0 themselves, but the values of sine turn out to be all 1. So what happens here, no matter which number L you would think your limit might be, when you get a small neighborhood of that number, when you get a small interval around L, you're either missing 0 or you're missing 1 from your values of your function, sine of 1 over x. So that tells me that you cannot approach a certain value L. You cannot have a limit because you're going to miss one of these, either 0 or 1. A small interval around L will definitely have to miss one of these two numbers. So for example, even if the interval is centered at 0, if I make it negative 1/2 to 1/2, I'm missing 1. If the interval is centered at 1, if I make it 1/2 to 3/2, I'm missing 0, and so on and so forth. So you're missing one of these two numbers. That's why the limit doesn't exist. So the limit really oscillates between, the limit values oscillate between 0 and 1. And actually one can prove that any value could be obtained as a limit value of some sort of sequence here of values of sine of 1 over x. So this is a very complex function. The limit doesn't exist. All right, folks. So we'll continue this discussion tomorrow. Tomorrow we're going to discuss about psi limits and things like that. And then we'll do a bunch of examples from the book here. So right now you're not quite ready to do the examples in a book because we still have to discuss a bit about side limits and such from this particular section. But tomorrow we will work on the examples on problems from the book, and we will discuss about these limits and their values. So this is where I am going to finish up my lesson today. If you have any questions, do let me know, folks. Otherwise, I will hope to see all of you tomorrow. So any questions here, folks? I'm going to stop the recording. All right, there's no questions.